Hello. Okay, so back for this part to talk about geometrical interpretation. Okay, so I'm going to go on what seems like a tangent, but it'd be really great if you could just stick with me here because what we need to prove first is that when we've got, oh, that is really small. Okay. Why is that? Oh, still really small. Okay. There we go. So when we've got, this sort of basic L-shape graph thingy that we've been dealing with this whole time. So when we've got a vector V and a vector W, and we sort of plot points out to make like a parallelogram that sort of encapsulates and adds these two vectors together. The area of this parallelogram is going to be equal to the base times height, right? So in this case, it's going to be equal to the length of W times sine of theta. And of course, in this case, this is going to be theta times the length of V. All right, so we want to prove that. So how would we go about proving this? Let's first think about what the area of this is going to be. So it's got to be base times height, right? Well, we know that the base is V, right? You know, that's the vector V. What we want to figure out is the height. Well, the height is going to be this length right here, right? We're going to say, y is the height. Well, how are we supposed to figure out y? Well, what we would do is we would say that sine of theta is equal to y over the length of vector W, right? Because sine is opposite over hypotenuse. So opposite over, and then hypotenuse would be this thingy. So if that's true, then we can multiply by vector W on both sides, and we can say that the height is going to be equal to length of W times sine of theta. Well, if we know that it's base times height, and we know that this is the height, then area is going to be length of W times sine theta times length of vector V. Now, what on earth does this have to do with interpreting the determinant geometrically? Well, I'm about to tell you. So let's go back to this idea of the determinant, AD minus BC. So what do we know? We know that this is the dot product of the vector negative CA times BD. And if you want to check that, just dot these out and you'll see you get this right here. Well, what are these two things? So BD negative CA. Well, if we go back to this A, B, C, D, negative CA is really going to be the perpendicular version of V, right? Because first of all, I should point out that we're going to call V AC, the vector AC, or call W the vector BD. Right? So this right here is really going to be the perpendicular version of V, right? Vector V perp. And this is just going to be vector W, right? So we can actually, let's draw this L out again with this sort of new information that we have. We've got V. We've got W. We now have V perpendicular. Okay. So, in other words, the determinant is going to be equal to this times this. Let's figure out the angle in between these things. We're going to call this phi, and we're going to call this theta. Okay. So, to figure out what phi is, well, we know this is 90, right? In other words, pi over 2. So if we just do pi over 2 minus theta, that would be phi, right? Okay, so we know that. So what we can then say after knowing that is we can say that V perp length times cosine pi over 2 minus theta times vector W length is equal to the determinant. The point is that we're sort of following this same format that we had here, right? The point is that the determinant is perpendicular V times W, right? But we've got to sort of deal with that angle in between. But that's not important. What we're going to say now is let's think about what we can turn this into. Because the length of V perpendicular is going to be the same thing as the length of V, right? Because we're just dealing with length. We're not dealing with angle or where it is in space. So we can say length of V. And what's cosine of pi over 2 minus theta? Well, that's just going to be sine of theta. We know this from trigonometry. If you have not covered that in trig yet, it's just kind of a rule times length W equals determinant. Now this should look familiar because what did we prove earlier? We proved that the area is also equal to this. So what does that mean? The determinant is equal to the area of a parallelogram, or of the parallelogram in question. Okay, so that leads us to a theorem, and it's going to sort of summarize everything that we just kind of said. So we'll use a different color. Okay, so we've got A being equal to these column vectors, V and W. Then the determinant of A is equal to length V times sine theta times length of W, right? Where theta is the oriented angle from V to W, with it being between these two values. So there are a couple of rules that we can say after saying that the determinant is equal to this. The first one I already pointed out. It's the area of the parallelogram that is spanned by V and W. But we can also say that the determinant of A equals 0 if vector V and vector W are parallel. I mean, if we think about it, that makes sense because, you know, the area, if they're parallel, well, there is no parallelogram, so the area is just going to be 0, so the determinant is just going to be 0. Now, the determinant, they also point out these facts, just things to keep in mind to memorize. It's going to be greater than 0 if theta is greater than 0 and less than pi. And then the opposite of that is true. The determinant will be less than 0 if theta is greater than negative pi and less than 0. Those are just kind of facts. So we're going to recap. We're going to ignore my little mental blurb here. But, you know, the basic idea is that we proved that the area of a parallelogram is going to be equal to this. And then we pointed out the determinant is also going to be equal to that, which means that the determinant is equal to the parallelogram that is spanned by the two vectors that are the column vectors of the matrix A. Now, we're next going to go into some examples. They're pretty quick examples. And hopefully won't have the little mental break that I had a minute ago. But we want to prove, is this matrix invertible? And then we want to interpret it geometrically. So the inverse of A, of course, is going to be equal to 1 over the determinant times D negative B negative C A. And of course, I'm not going to go through all of the steps of like basic multiplication here. We don't need to do that. But we get that the determinant is negative 5. So that makes it invertible. And then we get that the inverse is negative 1/5, 3/5, 2/5, negative 1/5. Right? So then how would we interpret this geometrically? What they mean by that is just what is the area of the parallelogram spanned by, and here we'll draw this out here. There are two column vectors, and that comes to this parallelogram, and our area is going to be, let's see, what's our area going to be? Oh yes, our area is going to be 5, because we take the length of that determinant and it is 5, so that makes our area 5. Pretty simple example, just putting all this stuff in practice. Okay. Another helpful example. We want to figure out for which values of the constant A is the matrix A equals 1 minus K 2, 4, and 3 minus K invertible. Well, we want to figure out, we're going to have to set the determinant. We're going to figure out the determinant, right? The determinant is going to be 1 minus K times 3 minus K minus 2 times 4. And we can have, this cannot equal 0, right? So we multiply this out. So we get K squared minus 4K minus 5. Once we multiply this out and factor in this part, If we factor this again, we get k minus 5 times k plus 1 equals 0. This is pretty simple. So what we know is that A is invertible for all real numbers except, of course, all real numbers in the subspace 2, except k equals 5 and k equals -1. This is kind of a good example of how, linear algebra brings in all different types of math. This is really something you would have learned in like algebra 1 and 2. You would have reinforced it in pre-cal. You would have used it just basically in calculus. So it's kind of a good example of how that sort of works and how it kind of reinforces everything you've learned in math so far. So we're going to move on to a final example. Okay, so we've got this reflection matrix. Got a reflection matrix, or we've got a matrix A that represents a reflection about line L. This is our line L. We want to use the determinant to verify that it's invertible and then find inverse of A, right? Okay, so a reflection matrix. By definitions discussed in previous lessons, we know that that has got to be equal to AB, B negative A, where A squared plus B squared equals 1. Well, now the determinant is going to be negative A squared minus B squared. And if we're using what we've already learned here, that's going to have to equal -1. So that right there proves that it is invertible. But then we actually have to find the inverse. So if you do 1 over -1, the determinant, times negative A, negative B, A, what you actually end up with is what you started with. You end up with A, B, B, negative A. And this is kind of a cool example because it's just like a cool little factoid to think about. Because think about how much sense it actually makes that the inverse of a reflection matrix is itself. Because if we draw, say we've got a line, and that line is the vector x. Another line, it's ax. So you can sort of move between these things freely, right? So let's say that we had ax and we were trying to move back to x. Well, that means that we would have a times a times x, right? Because we would be taking a times a vector x and then multiplying that times a again. Well, if vector x is equal to a times vector x, well, that means that these a's cancel each other out, which means that they've got to be inverses for each other. They're both they're both the same thing, but they're inverses of each other. So they cancel out. So that's just kind of, I mean, that doesn't really have to do anything, but it's just kind of cool how we can bring in those definitions of different types of transformations and use that and kind of apply that to invertibility and kind of find some cool things. But then they interpreted this geometrically, which I will do very quickly, and then we'll end this video and we'll actually move on to, we'll have some questions. We'll go over some questions from this chapter, problem sets, and then we'll have lesson 3.1, which is about image and kernel of a function, which is really fun to say, but not actually that bad. So to interpret this geometrically, we've got, this is our line L. We're going to start with random vectors. We're going to start with, in fact, we're going to use those handy little E vectors, those little identity vectors. And of course, we've got I over 2 here. So now they have us think about if we reflect over line L. So if we do that, we end up with this and that. Okay, so that means that this is vector W and this is vector V. And we can say that W is equal to A times E2. And V is equal to A times E1. And this right here is negative pi over 2 because it's been reflected over. Right? So in other words, we can actually say that the parallelogram spanned by V and W, this thing right here, is actually going to be a unit square, right? With area of 1 and theta of negative pi over 2, right? It's still going to be a unit square just like this was, right? And then the angle is just going to be reversed, right? So when we reflect it over the line, we're still going to have a unit square, and then we're going to have the opposite sign for the angle theta. Okay, I'm going to stop our video right now. Sort of to recap this whole lesson. Look at my notes. Okay. So to recap this whole lesson, we went over what inverse is in general. We went over this whole idea of using the identity matrix to find inverse, the idea of A times vector X equaling vector 0, only having the one solution if it's invertible. We talked about how to find the inverse of a matrix in two methods. The first method was to set it equal to the identity matrix. We talked about multiplying with the inverse. We talked about criterions for invertibility, proving that. We talked about the determinant, which led us into our second method for finding the inverse, which is using that 1 over AD minus BC times D negative B negative CA as the inverse. And then we talked about the geometrical interpretation of the determinant as the same thing as the area of the parallelogram spanned by the column vectors of A. That was a lot, but that was the basics of our lesson. And I will come back. We'll be starting with lesson 3.1. Thanks so much, guys.